All right, so here's the answers to page 8. I posted those in Google Classroom. You can go and see those. See what you need. So let me know if you can't do any of those. All right, so I wanted to show you one where what happens if there's one of the reactants that you just can't hold constant. For example, look at A. None of the two trials or two experiments are the same. But B is. So let's find A first. I think I would do that ahead of time from now on, but all right, so let me move that down. All right. Rate equals K times A times B. I'm going to do A first because if I do trial or experiment 1 and 2, you can see it's going from 0.5 to 1. It's doubling. The rate is going from 1.2 to 4.8. It is going 4 times by a factor of 4. So 2 to what power gives you 4? A is squared. So now we know the exponent on A. So what we would normally do now is pick 2 experiments where A is not changing, but there aren't 2 experiments where A isn't changing, but that's okay. It's okay because I can now just plug in whatever's happening to B and what's happening to A and see how that affects the rate. What do I mean? All right, let's do these 2. Now notice what's happening. A is doubling, but so is B. And the rate is going from 4.8 to 38.4, which once again, if you can't figure out by what factor, so 38.4 divided by 4.8, and you can see it's going by a factor of 8. All right, how am I dealing with that? Well, rate is going 8 times. A is doubling, and we know that that's squared, so that's why it works. Normally, we would say A is staying the same, and it doesn't matter what we raise the power to. Right? But now it's changing. It's doubling. But we know the exponent. So 2 to what power? Well, the power is a 2. Let me change my eraser. All right, but what about B? B we don't know. So B is also doubling. So 2 to what power? All right, so now we got to solve for X. So we are doing logs. Watch my other video tomorrow. You'll see there's logs. 2 to what power? 2 to the second is 4. So divide both sides by 4. So 8 equals 4 times 2 to what power? 2 equals 2 to what power? See, that's why it works. So now we know B is to the first power. So we said you have to have one staying constant, but you don't really. These are the a little more challenging questions, but not unreasonable. All right, we're going to learn something today called the integrated rate law. So the integrated rate law requires more calculus that somebody else did for you. You don't even have to understand, and that's okay. But I want to show you the background behind it and then show you where the equations come from. All right, so normally we would be doing lab experiments dealing with kinetics, and those lab experiments would be measuring some change that's occurring over time. We've been talking about putting it in brackets over time, which is molarity over time. And that would be if you have a change in concentration. All right, so how are we measuring right here this change in concentration? Well, it depends on what you're doing. Maybe you could get a color change. So something starts out red and then slowly fades to clear. So what you can do is measure using a spectrophotometer, measure the color change, or measure the absorbance at the first color, let the color change as the reaction goes, measure the absorbance as you go on. It's going to go down, it's going to be decreasing because you're measuring how the reactant is disappearing. Or the other way around, start with a clear solution that changes color as you produce the reaction. So now again, you can use a spectrophotometer, 0 absorbance in the beginning. As the reaction happens, it's going to get more and more and more and more absorbance as it gets darker. You could measure conductivity. Let's say you're producing lithium ions in the reaction. So no conductivity in the beginning, and it would increase in conductivity as you made more lithium ions. If you're dealing with a gas, you would measure pressure. So we have our pressure probes. And as I said, we normally would have done probably 3 experiments with this. And I'm going to try to figure, I don't want you just to watch me do a video of an experiment. I think that's kind of silly, but I got to figure something out just so you can see this stuff. All right, so here's the example that I always use because it changes color. So in the beginning, you're measuring Br2 aqueous, which is this orangish yellow You also have formic acid here, which is clear. So we're measuring how the change in concentration of Br2 changes over time. Eventually you get to clear. So all of the products in this reaction are clear. So what you would do is set the spectrophotometer at a particular wavelength of light. We want to use what's called the lambda, or the wavelength of maximum absorbance. And you measure the absorbance of the orange, which is going to eventually fade all the way to clear. So the reactive absorbance is going to start at some concentration and it's going to go all the way to zero eventually. But it doesn't do it in a straight line, as we talked about yesterday, or one of these days. So in the beginning, we could measure the molarity. Let's say at 0 time, so before you started, the molarity of Br2 was 0.0120. And so now you hit start and then the reaction starts. So now you can find what is called an average rate over a particular time, like maybe from 0 to 150. You would just do the average. So you take that plus that, divide by 0 to 100, and then you would get molarity per second as an average. You can also get the instantaneous rate at any particular moment in time, but in order to do that, you have to do some calculus. That was related to this graph that I talked about. So you can see there's our starting concentration, and they graphed it all the way up to 400 seconds. And we get this curve, this nice curve that's occurring. At 100 seconds, the rate is, the concentration of bromine is 0.08, and now the rate would be 2.96 times 10 to the minus 5 molarity per second. And it's changing as you go down. As the concentration of the reactant decreases, the reaction rate also decreases. All right, now we want to be able to write a rate law now based on this. All right, so there's some manipulation that we can do to this. And again, people have already done this for you. Chemists have already figured all of this out for you. But now based on a graph of concentration versus time, which we just got, we want to be able to figure out the rate law. This is something before I started teaching AP chemistry, I didn't even know existed. I always learned it from doing all the data and graphing. I didn't know there was a shortcut trick. And I actually learned it from another AP teacher, which greatly helps you guys. All right, so what they're showing here is a graph of rate versus concentration. So rate versus concentration. So now think about this. If we stick a K in there, now we have rate on the y-axis equal to concentration on the x-axis. So then what is the slope of this straight line? Well, it's K. And then plus B. Right? We got mx plus B, which in this case is 0. That's intersect with 0. Because when the rate's 0, the concentration's 0. You can't have a rate if you don't have a concentration. So now we can create a graph, figure out the straight line, figure out the slope of that straight line, and graphically calculate the rate constant. More so than that, even, you're going to see in these next few slides, we can actually pick out the concentration or the rate law just based on the graph. So now this is the table of constants and the equation sheet that you get to use on the exam. We're focused now on this bottom section of the first page, which is where the kinetics equations are. So I made that a little larger so you can see it. Now, we have learned so far that there is 0 order, there's first order, and there's second order, and there's third and fourth. We haven't gone beyond that. These are the only 3 you have to know, and most of your time is going to be spent with the first one. And the reason for that is half-life. Now, all of these have a half-life, but radioactive decay, which is what they usually use, so how radioactive, say, carbon-14 is measurement of half-life, and they're all first order. So they're all first order kinetics when you're doing nuclear decay. So that's where you usually see it, and that's what this is right here. So the only equation for half-life that's there is first order reaction half-life. 0 and second order reaction half-lives do exist, but they are all based on the initial concentration, and they don't make you learn them. So half-life is T1 half, which is how that is. So T1 half is based on the initial concentration for 0 order and for second order. For first order, it is not based on initial concentration. And if you look at the equation, there's no mention of the initial concentration whatsoever. But the other 3 equations are listed in order. Uh-oh, my screen's falling down. Hold on a second. There we go. Almost lost my lab. they're listed in order. So this is 0 order, this is first order, and that's second order kinetics. So those equations right there are what we can use to calculate anywhere along this curve, if we know whether it's first, second, or third. So once we determine that it's first, second, or third order, once again, once we determine that, we go to our equation sheet, and it goes, they don't tell you this, but it goes 0, first, second. So that's the order it's listed. And then the half-life is only first. All right, so let me go back to full screen here, and let me slide some of these in. So I should be able to grab these. No, I can't. Let me slide them in a little more. 1 second. Just want to be able to grab those so I can show you. Okay. Now, so one way of defining the rate is to use the expression below, and therefore the slope of a graph. So rate is equal to the decrease in concentration of a reactant over time. The decrease in the concentration of reactant over time. A 0 order reaction. So what we're graphing here on all of these graphs is concentration versus time. It's a concentration versus time graph. Concentration on the y-axis and time. All right, so if you see a straight line, it's a 0 order. So straight line graph, 0 order. Because what that means is the concentration does not affect the rate law. Right? 0 order means rate is equal to K times the concentration of A to the 0 power, which means, as you can see, the rate of A does not, or the concentration of A does not affect the rate. So y is equal to mx plus b slope. So the slope of the line is equal to the negative of the constant. First order, they are both curves. I'm going to show you both of those. See, the first order and the second order are both curves. How do we tell the difference? A first order graph will be a curve, but it will show half-life. So it'll show half-life. So what is half-life? Half-life is exactly what it sounds like. When that time goes by, whatever that half-life is, you have exactly half left over of what you started with. So here's a graph. Let me get rid of that. All right, so let's say we start at 1 molar. So molarity, concentration versus time in seconds. 1 molar. 0.5 molar took that amount of time. Looks like about 1.75. The next half-life, so 0.5. 0.25, half of that one. So another half-life. Notice it's the same amount of time. 0.125, half of that one, same amount of time. So it took, again, 0.06125, 0.03, get it? So half, 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 half. It's very consistent. That's how you know it's a first order reaction. So it's a first order reaction if the graph of concentration versus time shows half-life. Let me see what I have on this one that shows it a little more maybe. So once again, initial concentration, you'll see that A with a 0, they call that A naught, meaning at 0 time. So initial. So the initial concentration at 0 time. 1 half-life goes by. Arbitrary units. Could be 7 minutes. Could be 4 hours. It could be 1,000,000 years. But it's consistent. So we have a half-life divided by 2, then divided by 4, then divided by 8, then divided by 6. So 1 half-life, 2 half-lives, 3 half-lives. All right. So then if it's not a straight line and it's not a curve that shows half-life, then it's going to be a curve for second order. You won't have to go beyond that. You will not see a third order reaction. So rate equals K squared. Now this is a concentration or a graph of rate versus reactant, and I've included that years ago, but I haven't seen any questions relating that. This is just getting back to the equation, and I would rather you learn it from the equation sheet because this is what you get to use on the exam. I think it's beneficial to be able to arrange this into the y equals mx plus b format, and then it helps with the graph, and then it helps with what K is. because K can be now deduced from the graph. All right, so if I rearrange that, what we're always going to rearrange it in is Y is going to be the initial concentration, whatever we're including. Now, sometimes it's just initial, sometimes it's the natural log of the initial, and sometimes it's 1 over the initial. But that's going to be our Y. So if I rearrange that first one, so that's Y. So Y equals. So I'm going to rearrange it. So now that means I got to get that over to that side, or I got to get that over to that side, however you want to do the algebra. I'm going to bring that over there, and then I'm going to change the signs. Right, so when I do the algebra, I'm subtracting that from both sides, but then that gives me the opposite. So then I'm going to change the signs. So it ends up being KT. So if I leave the negative there, negative, negative, and now I have subtracted this from both sides. So negative AT, which is why I like to rearrange it. And that's what's up here. So you can see right here is our, they have it rearranged a little differently. Y equals mx plus b. Oh yeah, actually, that is the right way. Oops, went the wrong page. Sorry, I switched pages. Back to it. There we go. Now I said solve for this when I was wrong. That's why I was confused there as to why I was getting the wrong answer to what I wanted to do. So let's rearrange that again. Now, I was not thinking ahead, I guess, is what really happened there. Or I was thinking ahead about what I wanted to show you next. So I think I forgot something, but anyway, here it goes. So back to paying attention this time. So Y equals mx plus b. Now, what we know is we want to graph every time. This is why I messed it up. And as I was telling you it, I knew I messed it up, but I was coming back. Every one of our graphs is a concentration versus time, remember. So this is just concentration at any time, which is what that one is, which is why I know I messed up. So I'm not actually doing that. I'm going to add that to both sides, because this is a specific kind of concentration at 0 time. So we actually want to solve for the concentration at a time, which is what I should have known. Negative KT, that's why I knew it was wrong, because of the negative sign. And now we're adding that to both sides, so we get plus. And that also makes sense now, because if we think about this straight line graph, remember 0 order is a straight line of concentration versus time. So the y-intercept is the initial concentration. And then the slope is equal to the rate constant. Now rearranging the next one then again. So now we're adding that to both sides, and then rearranging, we're adding that one to both sides. So that's what I have up here. So again, just more of looking at more graphs again. So some more graphs. Now, one of the things you're going to see us do now then is we're going to graph all of our data as concentration versus time. So this right here is a question from your book. Exercise number 81. And it says the data below is collected for the following reaction. Now, they always give you a temperature because K changes as temperature changes. That's the Arrhenius theory, which we'll get to. So then all you have to do is go to Excel or go to your Google spreadsheet. You put in the data, and now you create the graphs. What graphs are we talking about? Well, it will be concentration versus time on the x-axis and the y-axis. The y-axis concentration. The next one would be the natural log of the concentration versus time. And then the other one is 1 over, the inverse of the concentration versus time. So let me show you that coming up as well, if that didn't make sense. All right, so I want to do a question from your book, number 53. This is one of the ones that we had to do for our homework assignment for this coming up for this test. Have this handy, or equation, and let me just solve it. So number 53, the decomposition of SO2Cl2 is first order in SOCl2 and has a rate constant. I don't like using that font. Again, there we go. Rate equals K times SO2Cl2. It says it is first order with respect to it. to the first. K is equal to, now here's something the College Board will throw at you, seconds to the minus 1, 1 over seconds. Sometimes the College Board will only give you the rate constant and not tell you that it's first order. So how do you know? Well, molarity per second equals K times molarity. Remember, you're dividing both sides and you get 1 over seconds. So there's another way to tell that this is a first order because remember, the M on the bottom is always 1 less than the overall order of the reaction. What is the half-life? All right, so T1/2 is equal to, so there's our half-life equation. 0.693 over K, which is 1.42 times 10 to the minus. Now this is 1 over seconds, remember, this is unitless. So you're dividing by 1 over seconds, which means we get our answer in seconds. 0.693 divided by 1.42 times 10 to the minus 4. So we get 4,880 seconds. So the half-life is 4880 seconds. How long will it take for SO2 to decrease to 25% of its initial concentration? This is a nice easy one because it's a nice half-life number, meaning there's going to be 50% left after 4,880 seconds. Then there's going to be 25 after another 4,880 seconds. So it's 2 half-lives to get us to 25%. So we're just 4,880 plus 4880. So it takes 9,760 seconds. So now we have a way to measure the rate of the reaction. We know how fast a reaction is happening, both initially and then after some time. 25% left, for example. Notice the wording of it too, to 25% of its initial concentration. All right, if the initial concentration is 1 molar, how long will it take? So now we're looking for time in seconds for it to decrease to 0.78 molar. All right, not as easy this time because it's not one of these nice, neat half-lives, but it is consistent and we know what K is. And so how are we going to do it? Well, that's what this equation is for. Remember, 0, first, and second. So now we're using the first order kinetics equation. We know the initial concentration. So the initial concentration is 1. And we're looking for how long it takes for the concentration at the time to get to 0.78. We just plug it in. So the ln of 0.78 minus the ln of 1 equals negative K, which is 1.42 times 10 to the minus 4, 1 over seconds, times time. And we're solving for time. I like to simplify this. Don't try to do the algebra, because when you're subtracting logs, I don't know if you know this, you divide them. Get to numbers first, meaning, and plus it's the ln of 1. So that's something we should know. The natural log of 1 is 0. The log of 1 is 0. The natural log of 0.78. And then divided by negative 1.42 times 10 to the negative 4, and we get 1,749.7 seconds. So a half-life takes 4880, but to get to 0.78 molar, it takes 1,749.7 seconds. So now we can calculate any other concentration or time that we know. As long as we know K and we know it's first order, we can just keep plugging it into this equation now, like letter D. So if the initial concentration, let me get rid of this over here this time. So if the initial concentration is 0.15 this time, so our initial concentration is 0.15 molar, we want to know what is the concentration of the SiO2 after 200 seconds. Same thing, we just use the same equation we just used, but now we're solving for the concentration of A minus the natural log of the initial concentration equals negative 142 times 10 to the minus 4 times 200 seconds, or 2 times 10 to the second. I like to simplify this, like I said, so I'll turn that into a decimal right away. So the ln of 0.15. So now I have the natural log of A equals, I'm going to bring all those over there. So I have negative 1.42 times 10 to the -4 times 200, or 2 times 10 to the second, divided by -1.8971. Write that as a natural log. So I get the ln of A is equal to 0.01497. Now remember what I showed you, how to get rid of ln's. So e to the 0.01497. And we get 1.02 molar. Now, does it make sense? Well, the initial concentration was 0.15. After 200 seconds, the concentration dropped to 1 point. No, that does not make sense. Did I mess up? That's why I always check. 0.15, what did I mess up? A number along the way, let me check. So ln of 0.15, -1.8. Oh, that was the problem, right? No. -1.42 times 10 to the -4. Yep, that part's right. Times 200 divided by, is that the right answer we got before? Divided by -1.897. I think I'm hitting a button on my calculator and it's not working out right. Because that does not make sense that it would go down that far after 200 seconds when the half-life was whatever that was, 4,000 something, right? Was that what it was? Oh, so let me think about this. Something's not right though. After 200 seconds. Let me just try it again. Let me just try it here in the middle. Let me see if I could be hitting something on my calculator wrong. That's one of the problems when you're standing here doing it by yourself when something strange like that happens. Why I know it's wrong. So do you see why I know it's wrong? If our initial concentration is 0.15, it's not possible for our concentration to go up to 1.02. It has to go down because we're using it up. But again, let's just plug it in. So it could be something simple. I could just be hitting a button wrong. Like I said, I'm going to use my handheld calculator this time just to make sure. So we're looking for the concentration at 200 seconds minus the ln of the initial concentration, which was 0.15, equals -k, which is 1.42 times 10 to the -4, and then 200 seconds. So 2.0 times 10 to the second seconds. So let me multiply this over here first. So 1.42 times 10 to the, so this is -0.0284 equals, oh, I see what I'm doing wrong. I've divided it. Hopefully you're yelling at your screen. I just figured out what I did wrong. So ln of 0.15, this is -1.8971. So there's that number again. So here's what I did wrong. So I divided, and that's why I was getting the wrong answer. But remember, this is subtracted. So that means plus the opposite. So now I'm going to subtract this from both sides, and I get the ln of A is equal to, subtract that from the other side. And I get -1.926. Now we do the e to the answer, and I got 0.146 molar. Yeah, so that was what I did. So I wasn't my syntax, my calculator. It was just me trying to go too fast and then, dividing instead of doing the algebra right. See, now that number makes sense. See, so now after 200 seconds, the molarity drops to 0.146. That's why I tell you when you're doing these problems, see if your answer makes sense. I knew something wasn't right with that first one, but again, it was just an algebra mistake. Oops. So what this is another question from the book. They give you the numbers. I took it and plugged it into Excel. Why? Well, because we're looking for the graph. So this is concentration versus time. So if I can do a concentration versus time graph, and I can check whether it's a straight line. Is it a straight line? Is it a curve? And if it is a curve, is it half-life or is it not half-life? And so this is the graph that I ended up getting. Let me get rid of some of this. So when I took those numbers, so there you can see them over there off to the side, and I plugged them in. So now we can evaluate. It's definitely not a straight line. I mean, I'm not going to try to connect the dots perfectly, but you can see it starts there and it's definitely curving. All right, well, what about half-life? Well, we could just look at the data. Half of 0.95, kind of close to that, 50 seconds. And then half again. After another, because if it was 50 seconds was half, this should be 0.25, and then another 50 seconds should be 0.125. So it's not half-life. So I'm going to guess that this is a second order reaction. Why? Well, because it's a curve and it's not half-life. Now, what I can do then is I can actually check it. So how do you check whether it's going to be, whether I'm right or not? So let me show you my graphs. So what I did was I didn't do a zero order because we already saw that that was not a straight line. So what I graphed over here was, actually, here's concentration versus time. And there we go, definitely not a curve, or definitely a curve. What I graphed over here was 1 over, I don't know if you can see, I shared my screen, so you should be able to see that. Let me, so right here, 1 over. So what this graph down here is a graph of 1 over concentration versus time. So the inverse, 1 over concentration versus time. Take a picture of this one. Oh, the right click doesn't work on that anymore. So notice the nice straight line we get. So a 1 over concentration versus time was a straight line. So going back to our kinetics, all the way back to here, when we first talked about this, remember what I said about first, second, third, or zero, first and second. So 1 over, it would be the ln of concentration versus time is going to give you a straight line. If it's 1 over concentration versus time, that gives you a straight line, then it's second order. So there's another way we can evaluate it. All right, so try some of those that I have given you, and let me know if you need more help.